Well, good morning, everyone. Happy Friday to you. It's good to see everyone here. For those of you who don't know me, my name is Darrin Thome, and I'm the Associate Regional Director for USGS's Southwest region here in Sacramento. It's great to see the attendance for today's Wildfire Science Workshop between USGS and the State of California agencies. And I understand we might have some Forest Service participants today too, so that's great. It looks like so today's workshop is covering the topics of land cover change and ecosystem response, and is the second of 3 being held in the next week or so. So as I mentioned at our first meeting, these workshops are the result of recent conversations between USGS and California Natural Resources Agency, and they're designed to promote greater connection between USGS science and the information needs of the state of California. So today we have 5 scientific talks, just like the last time, and each of which will be 10 minutes of presentation followed by 10 minutes of discussion. So our goal here is to provide a snapshot of various wildfire topics on which USGS has been working, along with an opportunity to begin a dialogue on each topic. So we encourage your questions after each presentation and look forward to a robust dialogue. So please don't be shy about questions. One quick request for you all, it'll help our bandwidth for this meeting if you turn off your cameras unless you're asking a question, in which case we encourage you to turn your camera on. So with that, I'll turn it over to Loretta Moreno with the California Natural Resources Agency for a few remarks of her own.
Good morning, everyone. May have seen all of you the other day on Tuesday when we had our first workshop in the same vein of topics. You know, we're just excited to have our second of 3 workshops on looking a little closer at USGS science. I know the workshop the other day led to a lot of offshoot conversations across science teams and agencies. And so we're hoping that the more we just know about current science and tools and resources and analytics available to us, that we may be able to tie into that work, build off that work. So we're excited to keep this conversation going. And please don't hesitate to ask questions today or reach out to the scientists speaking today with USGS, because I think they're eager to share their work. So with that, I'll pass it back to you, Darrin. Thank you.
Great, thanks, Loretta, appreciate it. So before we start our actual scientific presentations, we have some introductory remarks from Susan Benjamin, who's the director of our Western Geographic Science Center. So Susan.
Yes, hi, it's great to be able to meet with all of you guys. As Darrin says, I'm the director of the Western Geographic Science Center, and if you hadn't picked up by now, USGS is divided into many different science centers with different focuses. So we focus on geographic analysis. We're a relatively small center, but we have people throughout the West, including California and the big group in Arizona. So some of what you'll see presented, we're testing in Arizona or different other places than California, but we think we can relate it back to problems in California. Mm-hmm. So our science focuses on understanding what's going on at the land surface, as opposed to deep underneath, as some of our colleagues do. And we come from a tradition of mapping land cover and land use, and looking at changes in land cover and land use over time, and trying to understand the trends that we see. Most of our work is rooted at one point or another in remote sensing of the Earth's surface. So either Landsat or hyperspectral satellites or LIDAR or airborne imagery. And then we use some advanced GIS analysis to link either our data measurements or other USGS data measurements with other information to help understand processes and patterns. We've also developed many large geospatial database models that combine with climate models to look at the consequences of a changing climate. We're also used to scaling our work either from site specific to a regional scale, or in some cases from a coarse national or global scale down to regional or local implications. So we're really excited to present to you guys today. It's just only a subset of what we do, and we have a website that you can go to through the USGS homepage and find out other things that we're doing. But based on the discussions on Tuesday, I did want to mention that the subject of LIDAR came up, and pre and post fire LIDAR are things that don't happen together very often. And we do have access to one data set from the Pole Creek watershed in Oregon, where we've done some, one of our scientists has done analysis of that data, both pre and post fire in a coniferous forest. So if anybody's interested in that, I can get you together with Jason Kreitler, and you can talk more about that. So just send me an email or put something in the chat, and I'll be happy to set that up. I don't want to take time away from the scientists because they've got the real stuff. So let's move on. Thank you.
Thanks, Susan. Appreciate it. Yeah, we did have a robust discussion about LiDAR, so thanks for that follow-up. All right, so our first presentation is from Cynthia Wallace. She's from Western Geographic Science Center. She's going to be talking about the application of climate landscape response metrics to map ecosystem dynamics, especially related to vegetation composition. So Cindy, it's all yours.
Hi, thank you so much. It's really a pleasure to be here. I'm really excited to share this work with you. Climate landscape response, or CLaRe metrics, were developed for a project to help the National Park Service control bufflegrass in their landscapes in the Tucson area here at Saguaro National Parks East and West. And so the next few slides will share this background and how we are using CLaRe in our region. Next. Lisi? So bufflegrass is a serious issue in the Tucson region. The Sonoran Desert ecosystem is naturally fire resistant because the plants are widely spaced and fire does not spread easily. This is seen in the photo on the upper left. However, bufflegrass fills these spaces as shown on the right, forming a blanket of fine fuel that can carry fire broadly across the landscape. Control of bufflegrass is a high priority issue for managers in the region, and the use of herbicide is considered an essential tool, but it is only effective when the grass is at least 50% green. Next. To help managers know when and where bufflegrass is green, so I want you to think about understory vegetation that fuels fires in your area too. We explored relationships between MODIS satellite greenness data, observations of bufflegrass greenness collected in the field, and precipitation. And you can see these graphs. The top graph shows in green the field measurements and the red satellite measurements, and they show a nice relationship with those in this area that contains a lot of bufflegrass. Whereas in the bottom graph, you can see the blue peaks of precipitation preceding the field observations of green up. So with these data, this is how we created the climate landscape response metrics, which are the correlation coefficient between current greenness and prior precipitation amounts that are totaled over various time periods. And this is shown in the graph in the bottom left there. It shows CLaRe for ground-based observations in green and for the MODIS satellite greenness data in orange, calculated with the current precipitation on the far left, so not very strong correlations there, but then as well as with accumulated and total precipitation totaled over 1 through 8 time periods. And you can see the correlation increasing as you sum in more precipitation. And in this area with a lot of bufflegrass, you actually see it peak at about 5 days. So next. So we can take any one of these measures and we can map it across the landscape. And here we see mapped the pixel by pixel correlation between the current 8-day composited MODIS NDVI greenness and the total precipitation from the prior 3 time periods. And I want you to notice that these higher values of CLaRe in Saguaro National Park East here correspond, have a nice visual correspondence with the mapped patches of bufflegrass shown as little black outlines. Okay, next slide. So this slide, I want to spend some time with. This slide really captures the power of the CLaRe metrics. Using wall-to-wall mapping of bufflegrass that was accomplished in Saguaro National Park East in 2012, we were able to examine pixels with pure native vegetation and compare them to those that contain bufflegrass. So we started with the Southwest Regap vegetation map shown on the right, and we overlaid the footprints of MODIS pixels to identify the dominant mapped vegetation type within that pixel. We then used the polygons of bufflegrass mapped by the park to calculate an approximate % bufflegrass within each MODIS pixel. So the graph on the left shows the CLaRe values associated with the pixels of pure native vegetation. So CLaRe, you can see here, it is effectively stratifying the landscape according to vegetation types, separating it by rooting depths. So you can see the forests are at the bottom with low CLaRe values, and the scrub and grasslands are at the top with high CLaRe values. And this is across all those summed periods of precipitation. It makes sense that deeply rooted vegetation is not as responsive to recent precipitation and vice versa. But more exciting in our region, you can see in the graph on the right there that the CLaRe metrics reveal the presence of bufflegrass within a vegetation community. And here we're looking at the Sonoran Palo Verde mixed cacti desert scrub that hosts a saguaro cactus. The bufflegrass, the reason that it is revealed is bufflegrass greens up so much quicker than native vegetation after it rains, so that even small amounts of bufflegrass within that ecosystem dramatically shift the CLaRe metrics to higher values overall. So in our region, bufflegrass acts as a problematic fuel in the desert, but it seems likely that CLaRe would be effective at highlighting problematic understory vegetation that acts as a fuel in the forests of California. Next slide. So in our area, the application that we're doing right now, we're trying to inform timing of treatment using near real-time data. So the way this protocol works is we can use the greenness data. We use the observed field greenness data to solve the linear equations that produce the CLaRe correlations for the amount of precipitation needed to trigger at least 50% green up in bufflegrass, which is the level needed to treat it. In our area with current data, a conservative answer is just under 2 inches of rain over a 24-day period will produce at least 50% green up in 8 to 16 days later. So we use this knowledge to guide herbicide treatment as shown in the graph at the bottom. First, the cumulative precipitation over 24 days is monitored, shown as the dashed magenta line. The blue line is the daily precipitation. And when you observe this total exceeding the threshold of 1.8 inches at the vertical red line, you predict bufflegrass will be at least 50% green 8 to 16 days later in the gray shaded area. On the day of treatment, you verify that green up has occurred using MODIS data. Next. So to translate this protocol from a single point to the landscape, we use gridded data to identify and assign values to the pixels that show this dynamic green up. That have enough prior precipitation and in the park that are located where bufflegrass has been mapped. Next. So here's what it looks like on the landscape. So this is the start of this year's monsoon season, 2021 monsoon. And in June, the landscape is super quiet. And then in July, we start to see widespread green up in response to the monsoon rains. And these data are being served weekly to park personnel. And you can see on the left how the pixels are valued. So a maximum value of 123 is a pixel that had been mapped with bufflegrass in it within the park that got over 1.8 inches of rain, and that was showing some strong green up dynamics. And again, in California forests, it's likely that a similar near real-time protocol could be calibrated to highlight areas with shallow rooted vegetation or understory that are greening up dramatically in response to recent rain. If these areas of green up occur prior to the fire season, they may be considered higher risk for potentially drying out and being there to ignite and drive some wildfires later in the season. Next. And in fact, if we just explore a little bit, this is a study just to look at the potential for CLaRe metrics to map forest ecotones. And here in Arizona, I'm looking at the ponderosa pine vegetation type along the Mogollon Rim. We calculated CLaRe values for 8 years, stacked those images together, clipped them to the ponderosa pine vegetation type, and then input those data to an unsupervised classification to produce 20 clusters as shown on the right map, which are then examined. Next. And what we see with these 20 clusters, you see in the graph, which shows the CLaRe values for each year for the clusters that were created by the classification, by the classifier. You can see that there's a gradation from classes with overall lower CLaRe values to overall higher CLaRe values. And since we saw that CLaRe will stratify the landscape by overall vegetation rooting depths, these classes are identifying regions within the mapped ponderosa pine forest that contain different mixtures of canopy and understory. And I pulled apart the kind of extremes here. Class 20, the white class, that is it's mapped as white and it occurs along the northern edge of that area where the ponderosa pine is grading into the Great Basin grasslands. We see sparse trees and quite a bit of shallow-rooted grasses showing, whereas in class 4, that is mapped as red, it occurs in the heart of the mapped ponderosa pine, and we see just dense tree canopy. So it's important to note that CLaRe can be calculated on an annual basis, as we did here, or you can calculate it seasonally. And mapping understory that is dynamic and greening up in the spring, for instance, prior to the fire season, could potentially highlight areas for potential management intervention, whereas understory that is dynamic after the fire season may not be a problem, may be just important for wildlife habitat. And I also want to highlight that we have developed a method to calculate CLaRe on a Landsat scale at a 30-meter pixel resolution, in addition to the regional 250-meter MODIS-based. Next. We can also use CLaRe, to monitor yearly landscape condition. So in this application, we are using CLaRe to alert us to newly established populations of invasive bufflegrass. So we're back to the Tucson area here, but it's important to catch invasives early. And here, this protocol, we clip annual CLaRe metrics to a single vegetation type. In this case, the Sonoran Palo Verde mixed cacti desert scrub that hosts the iconic saguaro cactus and is susceptible to bufflegrass invasion. For
Hey,
each
Cindy,
year, yeah.
We're at past our 10-minute mark. If you could wrap up, that'd leave times for some questions.
Okay, all right. Well, this is just showing that you can have normalized CLaRe and you look for areas that are acting average and then jump. So so anyways, I've shown you these different next slide. So we've got CLaRe metrics and I showed you how it was calculated and the different things that it can tell us. I just want to say it's been really gratifying and exciting for me to watch the science be used in our area, and I hope that I've helped you see some ways that CLaRe can be applied in your landscapes. So thank you, and yeah, let's have a discussion. Questions?
Yeah, thanks for that, Cindy. Didn't mean to rush you there.
No, it's okay.
Yeah, so there's a lot of promise in how this could be used in forests in California, and we'd sure like to hear questions from participants on what they think of this, how it could be used, its application, etc. What questions do you have for Cindy? Either raise your hand or feel free to put your question in the chat. And Adam.
Hey, how's it going? Thanks for this presentation. Really interesting. My question is more of a practical question, I guess. Like how much work does it take to do this? Like on so you're kind of showing statewide things and then zoomed in things. If you're going to do this like statewide, you have to calibrate the different vegetation types, I assume, or like how much work actually goes into that, or is it as simple as like you just throw this up on Google Earth Engine and then we can run it, or what do you think?
Yeah, so at this point we do have the models a lot of it is Google. The near real-time stuff is a little bit trickier. It's Python based, but it's still automated with programming. But the annual and seasonal CLaRe metrics that are more historical, those data are in Google Earth Engine, and the programs are there to run in Google Earth Engine. As far as, if you had a problematic understory vegetation type and you wanted to catch it like buffalo grass, at a certain time in its phenology, that would require, in our case, we had some citizen science data. We had recruited people, and we ourselves observed buffalo grass over a period of time in order to understand how much precipitation we needed to trigger the amount of green up that was necessary for the treatment. So if you have that kind of a question, it would take time to collect those data and develop those relationships. But as far as the ponderosa pine example where you're clustering the landscape, that can happen pretty quickly. It's a question of shifting the models to look at California instead of Arizona, that kind of thing.
Yeah, okay, because I'm just thinking maybe this could be useful for tracking like conversion of landscapes after wildfire, or like recovery after wildfire, so you could see maybe how long is it taking for the trees to come back. Is that something you think this could do?
Yeah, absolutely. One of the applications that we are looking at here is well, I guess this is a parallel thing, but yeah, because the CLaRe is going to give you a measure that's related to overall rooting depth of the contained vegetation. I think it would be really useful to look at CLaRe over time and to see, you would expect to have really high CLaRe values initially after fire as understory vegetation kind of takes over, but then as the trees start to develop, you would expect to see a shift to lower CLaRe values. And I was going to say another thing that we are looking at for the park is using CLaRe to quantify effectiveness of treatments that they apply. So if you are looking in our case to control and to eradicate buffalo grass, you would expect CLaRe values to decrease after your treatment because you are getting rid of that really flashy vegetation type.
Thank you.
Yeah, thanks for the question. Looks like we've got a question in the chat from David Gurman. He asks, or he says, if we were interested in timing of green up across the landscape, it's a wildlife management question, over the past 20 years, would that be possible? Our rainfall varies considerably from year to year, and we would like to understand how timing of green up relates to demographic variables.
Demographic variables with the wildlife, I guess.
That's correct. In other words, the idea is that green up varies considerably. We get these greening rains, but they may come in October, November, December, January, February. So there's a wide variability when the green up occurs, and it would be really nice to understand it'd be nice to understand exactly what the timing is, and then relate that to how our lambing rates are, for example, or our population, our survival, and things like that.
So I think in my next presentation, I think that there is a graphic that might be perfect for what you're looking at, that is looking at the greenness anomalies over time. With CLaRe, I think what it would allow you to do is, I think it'd be really interesting actually to look at seasonal and annual CLaRe to map the landscape into its different components and to see if there are certain areas that are favored for lambing, because I would think that the not just the timing of the precipitation, but also the composition is important. But then within there, which things are getting more or less precipitation. But I think in the next presentation, I'll try to remember to like show you which graphic that I think might be really helpful to answer that question.
That is an interesting question too. We look forward to hearing more about that, Cindy, for your next one. Elijah Portugal has his hand up.
Yeah, thank you. Can you guys hear me okay?
Yep.
All right. Well, thanks a lot for the great presentation. I was just kind of wondering if you thought that CLaRe or a similar kind of approach could be applied to identifying understory plants that are being irrigated relative to non-irrigated or natural surroundings, with the idea being that, you know, these irrigated plants would have a greenness value essentially unrelated to precip, where the surrounding veg would be responsive to precip, and just thinking about it in the context of trying to identify illicit cannabis grows that are on, you know, often in places where there's dense conifer forest as the overstory. But yeah, just kind of wondering if to hear your thoughts along those lines.
Yeah, so the in our area, like on slide number 9, where I show the you know, where we are trying to do a near real time modeling, you can see in June, well, it's kind of hard to see, but in June, in the top ones, you can see some pixels that are in the purpley color that are in the northwest there, and that's all agriculture. So you're getting dynamics that are unrelated to precipitation. So I would think that you know, irrigated cannabis would show up similar to just any old agriculture. So yeah, you do get what you'll see areas like that where you've got green up dynamics unrelated to precipitation.
Thanks for the question, Elijah. Any more questions? We've got maybe just a minute or so before the next presentation. Okay, we can shift gears for your next presentation, Cindy.
Okay, so the next model I'm going to share with you is the fallow land algorithm based on neighborhood and temporal anomalies, or FANTA, which is like the best acronym ever. Okay, next. So FANTA was developed to automatically map planted versus fallowed agricultural fields in the Central Valley of California. And the model uses 3 inputs shown here: the MODIS, again, MODIS Normalized Difference Vegetation Index, or NDVI data, the same as the CLaRe. And 2, a mask of cultivated lands that we derived from the USDA crop data layers, and 3 NOAA climate divisions that serve as neighborhoods, given that the same crop is likely not suited to different set of climate conditions. So using these data, we calculate a set of temporal and spatial anomalies and compare these to the greenness condition at any pixel using 4 questions. So next. So for temporal anomalies, we look at the historical values at each pixel for each 8-day MODIS composite period since MODIS began in 2001, and we assemble them and capture the median value. And all pixels above that median are considered to compose a pure crop signal. And the mean and standard deviation of those pixels are extracted and composited for each month. So, and likewise, we do that for the spatial anomalies. We consider all the cultivated pixels within a climate division neighborhood that are above the median greenness value to be, we consider that they're pure crop and extract the statistics for each month. And the current pixel is then compared to its history as a crop and its planted neighbors for each month of the growing season. Next. So the FANTA model asks 4 questions. It asks, based on your history, do you look or act like a crop? And compared to your neighbors, do you look or act like a crop? And if the answer to any 2 of those 4 questions is no, then we don't think it's a crop and the pixel is classified as fallowed. Next. So here's the resulting FANTA classification for 2014. And we show NAPE aerial imagery displayed to the right of the zoomed classifications for comparison. The accuracy was assessed using field validation data from 2014 and is shown in the table on the left. And the overall accuracy is good at about 86%. Next. So the binary FANTA classification produces and is fine for the agricultural application that we just looked at, for which FANTA was developed, but it produces and uses these intermediary maps of temporal and spatial anomalies that themselves are useful. So in this example, we use the FANTA temporal anomalies to inform this study to map wetland status and trends for a NASA-funded ecological forecasting project focused on the network of remaining highly managed wetlands in California's Central Valley that provide critical habitat for migratory birds. Next. In this case, we're mapping here the maximum greenness observed in April across 8 years along the top. And then in the bottom, we display the deviation from the 17-year mean value to see how each year compares to the norm. The bottom insets here show 2 wildlife areas, Gray Lodge in the northern part of the Central Valley and a portion of Los Banos in the central part. Next. By fitting a line to the monthly values across the whole 17-year history at each pixel, we can extract the slope and quantify the overall trend in greenness as shown here. We can easily see the stable landscape shown in gray, increasing greenness shown in red, and decreasing greenness shown in blues and purples. April here stands out, the month of April, with much of the 2 featured wildlife areas showing increasing greenness across the years, likely due to the advancing of spring that has been documented over much of the Northern Hemisphere due to global warming. The patches of increasing and decreasing greenness that are evident in the other months highlight areas that may be evaluated for potential management interventions. So a way to alert you to areas that are changing. Next. Okay, now in this application, this is another one, we are using temporal anomalies. We're back in Tucson and looking at the landscape status. And this is what I think might be helpful to look at the wildlife question from before. So what we are looking at here are vertical film strips where each strip represents a year. So you've got 2002 on the left and 2020 on the right, and each frame captures the Tucson areas shown in the map to the left. The year is represented by 46 frames, and you can see the months of the year listed along the left edge there. And each frame is a MODIS 8-day NDVI composite image. The colors in the frames are the percent full greenness range. And this is a number between 0 and 100 that shows where the current greenness of a pixel is relative to the minimum and maximum greenness observed there across 19 years of data, displayed grading from gray at 0 through green and into blue at 100%. So this displays allows you to visualize a great deal of data at one time. And what pops out here, you can see where the monsoon kicks in. So usually the 4th of July, around there, the monsoon rains kick in, and you can see the greenness, and you can see years where the monsoon was early, years where it was late, years where it didn't happen very much at all. So so this is like I said, a way to see a great deal of data at one time to visualize it. Next. So we're also using these data to map the status of the fine fuels at the start of the fire season. So you can imagine that this could apply really directly to your situation in California. But we're looking at the maximum greenness in that top box, which is the spring green up. So all the green up in response to the winter rains, and then comparing it to the maximum greenness in the lower box, which is the dry summer. So through mid-May to mid-June. And the difference there is how different the fuel is, how dry it is. So next. And here's what that looks like mapped for 4 years, 2017, 18, 19, and 20. And you can see how different the years are. And in the inset into the left there, I have actually mapped in the forest and the woodlands in our Sky Islands that surround Tucson. And this is just n equals 1, but if you do the next slide, we can see where the bighorn fire ignited due to lightning strike. So there's the bighorn fire in the landscape, and it's in an area that this status of fuels at the start of the fire season that this measure shows were really ready to ignite and adjacent to these forested ecosystems. So,
hey, Cindy, you get 2 minutes. Just letting you know.
Okay, well, I think I'm done. So the next. So in summary, the FANTA algorithm, it's a binary classification, but it creates these derivatives in order to ask the 4 questions. And the inputs are pretty easy to obtain and simple. The models, like you said, they're out on the they're in Google Earth Engine. It's cloud computing, so you can crunch a lot of data all at once. It compares the current greenness of a pixel to its historical greenness and to its neighbors. And it can tell us, it can classify landscapes into these binary planted versus fallow, but it could also be translated into another extreme condition like flooding, for instance. It can tell us stable, increasing, decreasing landscapes based on trends. So we saw that with the wetlands in the ecological forecasting project. We can look at the current landscape status using a % full greenness range. So calculating the condition of the landscape calibrated between its minimum and maximum, and then the status of the fine fuels at the start of the fire season. So hopefully you can see that there could be a lot of applications for the forests in California.
Thank you, Cindy. So questions for Cindy on the application of this model. Again, feel free to raise your hand. There we go. Adam Moreno.
Yeah, thanks. So actually, this is something I could use for agriculture right now. So you said this is already up on Google Earth Engine. Could you share the code, maybe in the link or something, or in a follow-up email? Because it's probably something I will look at today. And can it get like seasonal, or is this annual, or is this just one like long-term average composite, or what are we talking about temporally here?
Okay, so the way the FANTA model works is the MODIS-based model uses the MODIS 8-day composite image, and for each month we select the 4 images that best represent that month. And so then the temporal anomalies, you look at those 4 images and you extract the pure crop signal. You look at the maximum of those 4 images for a month to get a monthly maximum. And then you look at the dynamic range of those 4 images. So the min versus the max, because you expect crops to be pretty dynamic throughout their growing season. And then when I look at a pixel, I look at a pixel to map it as planted versus fallowed. I look at the months of May, June, and July in the heart of the growing season. And I also look at April, May, and June for an early growing season. And then I calculate the monthly. So it's like, you look at you capture the monthly statistics, and then you just say, throughout the growing season, were you looking and acting like crops, like when you were planted, so I don't know, I guess the the cropped, the model right now, I guess it goes to 2016. So, it'd have to be modified in order to pull in more of the additional years worth of data. But yeah, it's looking month to month kind of thing.
Thank you.
Okay. I can send you the paper.
Thanks for the questions, Adam. Does anyone else have any questions? We do have ample time. Let me ask David Gurman if we sufficiently answered his question regarding the timing of green up and if it's relatable to demography over time.
Yeah, I think the chart that she was sharing looks like that type of an idea may work. I mean, I'd have to look into it a little bit more, obviously, but that the green chart with timing of green up, I think we'd show much more variability based on what I know about our landscape than what it shows there. Yours is pretty consistent, and I think ours would vary over months as opposed to the very minor variations. But I think that would actually give us the capability to do what I'd like to do.
To look at the percent full greenness range for your area?
Right, really to understand, are we seeing a year where we're seeing green up as early as, as even December or January, or are we looking at a late green up where it's out in the maybe the March or April timeframe? Because it's a drought deciduous type landscape, which lots of desert landscapes are, of course, and so the timing of that green up matters a lot in terms of how bighorn sheep respond in our landscape.
Yeah. I was thinking that something like this might really help capture that.
And just as following up, so it sounds like this is all I guess it's coded. Is this also coded in Python? So this is all based on ARC and Python, and to derive these FANTA values. Is that how you would do that? And is that something that would be readily available?
Well, the FANTA, this stuff is it Google Earth Engine and scripts that I guess they are Python scripts, right? That run. I'll have to ask my programmer those details, but
okay.
Yeah.
Thanks for the dialogue, David. Does anyone else have any questions or comments for Cindy?
So here's a quick one. I noticed that at least on some of your cropping, you're fairly heavily dependent on the USDA crop mapping. One, I know that some of us have had critiques of its accuracy in a lot of locations. Has that impacted the results particularly? And what would it take if we wanted to substitute an alternate source of crop mapping data?
So yeah, on slide 15 there, I guess it shows. So the way that I created that cultivated mask at that when I was doing this study, so this one was published, I think in 2017. So, well, first of all, I think the USDA mapping is improving over time, but at that time there were, concerns. And so what I did was I used 7 years worth of data from USDA. And then I said if it was mapped as I separate out row crops and perennial and whatnot. If it was mapped as a row crop in 5 of the 7 years or 4 of the 7 years, I can't remember exactly what I used. So, but it was a statistical thing over a time period. And basically what that does is it just limits the universe so that I am looking at cultivated pixels. And so, I don't think that it affects the FANTA model because I think that as long as the universe isn't too big, I can still extract a pure crop signal, which is what I was looking to do. But it'd be pretty simple to substitute in a different map for that universe. I mean, it really is just a mask that you put in. So you can do that easily.
Thank you.
We have time for more questions. Any other thoughts or comments? Feel free to raise your hand, put a question in the chat, or just pipe up. Going once, going twice. All right. Cindy, thank you so much. We really appreciate your time.
You're welcome. It was really a pleasure to share all this with you.
All right, we're going to shift gears and we're going to be hearing from Ben Sleeter, again with the Western Geographic Science Center, and he's going to be talking to us about the Lucas model and its use in understanding land use change and fire effects. So Lucas, take it away, or Ben, take it away.
Thanks, Darrin. Yeah, okay, so I've got a number of slides here. I'm going to be approach this from a pretty high level, touch on some of the things we've been working on over the years, and try to leave enough time for some discussion. Go ahead and go to the next slide. Just a couple of people here to acknowledge Jin Schwinn, Paul, Jason. They've all been actively working on various implementations of Lucas. Jin Schwinn's done some work where we're linking erosion deposition models to help improve some carbon dynamics. Paul's applied the model across Hawaii for a number of research projects. And Jason's been doing some cool work with land use projections and its impact on conservation. Go ahead and go to the next slide. Okay, so what is the Lucas model? It's the land use and carbon scenario simulator. And in essence, it's a fully coupled model of land use, land cover change, and ecosystem carbon dynamics. We try to cover all major ecosystem or land use land cover types. We include a wide range of transition types that can occur on the landscape. Typically, we produce annual simulations. The model can be run across a range of different spatial resolutions, different extents, and kind of one of the big parts of our work is using Monte Carlo methods to characterize uncertainty. Go ahead and go to the next. So just quickly, I wanted to mention that Lucas runs in a programming or a software environment called SynchroSim. It's got it can run on a laptop running Windows. It's got a very nice UI that's been developed over the course of many years. This platform all originated back with landfire VDDT models, still supports VDDT, but the model can also be deployed in high performance computing, supercomputing environments. There's a lot of support for parallel processing to enable large simulations across large landscapes using a lot of cores, running many Monte Carlos. The model can be developed and interacted completely within the UI. It's also got a R package on CRAN that allows you to develop entire models using R if you want. There's also a Python package that's in development as well. Go ahead and go to the next slide. Okay, so from the land use land cover side, what we're using is a state and transition simulation model. Basically, we take a landscape, divide it into some discrete classes, like you see on the right there, a very simple land use land cover classification scheme for California. The boxes on the left denote those classes. Those are called states. The little diamond gray colored areas are the transitions that we're modeling here, things like urbanization, agricultural expansion and contraction, fire, drought, forest harvest, etc. When one of those transition occurs on the landscape, it can change the state class or state attributes of the model, and this is all done can be done spatially explicit. It can also be done in a spatially referenced type environment too. Go ahead and go to the next slide. From the carbon side, I won't spend much time on this. We've explored lots of different options to estimate ecosystem carbon balance, from simple lookup table approaches to using process-based models to derive parameters. More recently, we've integrated the carbon carbon budget model of the Canadian forest sector. So CBM CFS3, it's a model that's been used all over the world, developed first by the Canadian Forest Service. But it's a general modeling kind of framework that we've deployed here in Lucas, integrated into Lucas, to model the fate and transfer of carbon through ecosystems. Go ahead and go to the next slide. Okay, so in California, we really got started several years ago in support of the fourth climate change assessment. And what we were asked to do was to develop land use projections, land cover projections, which would support Leroy Westerling's fire modeling. And we did that. Our land use projections were largely based on historical land use, historical population, as well as some population projections developed by the Department of Finance. In turn, we ran the model for 4 different scenarios, 1 kilometer resolution, and the 4 scenarios generally being a low, medium, and high population projection, along with what we call a business as usual land use. The historical and projected percent vegetated data sets that came out of those runs were passed over to Leroy. He developed wildfire projections. In turn, we pulled back those wildfire projections and reran the model with his fire stuff. So the total scenario universe here consisted of the 4 land use projections. We ended up running RCP 4.5 and 8.5 as simulated by 4 different climate models in California. And all of those simulations, so that N of 32 different unique scenarios, we ran 100 Monte Carlo iterations of each one. Go ahead and click next. Some of the stuff we've been doing as part of the PyroGENS consortium is to improve this coupling here. So right, initially this was just kind of a linked approach. Now we're working on having kind of this dynamic annual coupling between land use and the statistical fire models. Go ahead and go to the next slide. Just quickly, some of the output that we got from the land use side. If you look on the left, this is the annual amount of, the mean cumulative transition area on the left for urbanization. You see the 3 population scenarios, low, medium, and high, and then the business as usual being actually providing the actual highest amount of urbanization out to 2100. You can see that for ag expansion, contraction, and then what we generally just call management, but including forest clear cut and selection, as well as orchard removal. Go ahead and go to the next slide. And if you want to look at a state class now over time, for example, developed in the bottom right corner, you can see the trajectory of the total developed areas. This is land use composition across the 3 population scenarios, as well as the gray line and ribbon showing the business as usual projection, again, out to 2100. And you can see the fate of all the other major land use land cover classes that we simulated in the model. Okay, next. In addition to land use and land cover, we also simulated a couple of disturbance types here, notably fire and drought-induced forest mortality. Fire, again, being the projections derived by the folks at University of Merced. And here we're just showing, again, the fire did not appreciably change under the different land use projections, but did between climate model across the top and RCP. Drought mortality, we developed a statistical model using some drought indices. Dave Marvin at Salo Sciences developed that method, so we included drought mortality here as well. Go ahead and go to the next slide. Oh, I lost my background on the right side. Those are going to be hard to read, but the 3 static maps here, this is just an example of some of the output we get. But for a given scenario across the 100 Monte Carlo iterations, the first of those 3 maps show the probability of development. agricultural expansion in the middle, and agricultural contraction on the right side. Again, just examples of the types of maps that are able to be output from the model. The animation on the left showing decadal changes in these primary land use land cover types. Obviously, we're not seeing the effects of fire and drought mortality only because we're not seeing changes in the underlying cover type as a result of those. There are some exceptions to that. But again, just giving you a sense of the dynamic projections. Go ahead and go to the next slide. Okay, so now when we think about carbon, again, carbon's kind of coming along for free when we do these land use projections. Here we've plotted the source sink from various activities. So you've got in the gray bars, these are the inventoried emissions, and then the colored bars are the sources or sinks from ecosystems. So you can see them in contrast with the inventoried emissions, positive values being a net source to the atmosphere, negative values being a sink.
Hey Ben, you've got about 2 minutes left.
Yep, next slide. Quickly on the left, this is total ecosystem carbon in box A. Again, just showing the trend, but this is the mean and the confidence intervals across all 32 scenarios that we ran. Kind of interestingly, we saw, and it's shown on the right here, that when you switch from a high to a low land use scenario, there's a pretty reliable increase in the carbon sink, whereas just shifting from, say, RCP 8.5 to 4.5 yields a little bit more uncertainty. That's that emission reduction bottom plot on the right side. But limiting land use conversion was quite reliable in these simulations. Go ahead and go to the next slide. We've also used the model to look at the effects of natural climate solutions on carbon storage. How can these different mitigation actions in the land sector increase carbon storage? How does delaying implementation impact those carbon benefits, and what are some of the economic costs and opportunities? We looked at several of these different kind of more discussed mitigation actions, and then we can plot the relative benefits from a carbon perspective on that. There's a Next 10 report as well as a paper in review right now documenting these. Go ahead and go to the next. We've begun applying this model now nationally. This is forest carbon. This is the net forest carbon sink across all U.S. forests. The model can also be used for sensitivity analysis, where we withhold various parameters in the model to try to better understand the major controlling processes at play of carbon storage. Go ahead and go to the next slide. And more recently, we've been taking a big step into increasing the spatial resolution of the model. A lot of the work now we're doing is going down to the native 30 meter resolution of a lot of the input data sets. This is Tuolumne and Mariposa counties at 30 meter resolution between 84 and 2000. You can see the effect. This is carbon net source sink here. Gray areas being a sink. This is the rim fire.
And we do need to wrap it up.
Yep, last slide. And so I just wanted to quickly mention, if you're not familiar with the Pyrogens Consortium, we're a partner in that, developing land use, land cover, and carbon projections to better understand and quantify wildfire risk. Again, I mentioned the fully coupled model with Leroy's work. There's going to be a set of long-term projections, land use, land cover projections, as well as some fuel treatment scenarios, which are all going to go into supporting the 5th climate change assessment. That's all I've got.
Thanks so much, Ben. Great presentation. Who's got questions for Ben? Feel free to raise your hand, put it in the chat, or just pipe up.
Hey, good morning. This is Nate Roth, the Department of Conservation, and I thank you, Ben. It's always wonderful seeing the stuff that you're working on and having the chance to occasionally bring it into some of our own work. I'm a little bit ashamed that I don't know the answer to this off the top of my head. With the high population scenario, what was it about that one that made particularly its agricultural trajectories differ so markedly from the other sets of scenarios?
Yeah, so good question. Lisi, probably if you can go to that one, you just go to the right one slide there. I think that it's easier to read when we look at composition here. Yeah, so important to note, the population projections, we decided that they would only drive changes in the urban landscape or the developed landscape more generally. So the three different population projections were linked directly to the rate of urbanization historically, and then used to make a projection into the future. So on one hand, you have the effect of those population projections and development replacing agricultural lands, as we've seen historically. But what we also have at play in the model is agricultural dynamics, expansion and contraction of agriculture, not related to urban or developed expansion. And so what we did for some of these other transitions, like agricultural expansion, is we, to represent a high, quote unquote, land use scenario, we sampled from the historical rates of agricultural expansion, targeted the years that kind of had the highest rates, and implemented those as our future scenario. Same thing with the lows. So I guess the long-winded way of saying that is that the agricultural expansion are somewhat decoupled from population projections generally. Does that make sense?
Yeah, it sounds like you basically, in establishing the criteria for the model, in the high, you picked high ag expansion as a driver in addition to the higher population side of things, and that's probably what we're seeing here.
That's correct. Yeah, that's correct. And keeping in mind, right, that with high population growth, you still have you have an increased rate at which you're replacing agricultural lands as well. But yes, the high scenario was first geared around developing the population and urban or development projections, and then also mimicking a high land use utilization as well. So expanding agriculture at a high rate.
Thank you.
Yep.
Thanks for the question. Nadia Tace, that's the next question.
Hi, this is Nadia with CalFire. I just was wondering how the conservation scenarios account for the trade-offs with wildfire risk or leakage from increased harvest elsewhere to account for our high wood consumption in the state.
If you can scroll down, Lisi. In general, it didn't. We in the conservation. Let's see. So the bottom left slide there. Thanks. So the only one here where we're really changing the types of forest management was the CFM scenario, or changes in forest management. And here all we did was change the mix of clear cut and selection harvest. But across all the other scenarios, these were compared to a baseline forest harvest rate, which was kept constant with historical data. But we didn't consider the effects of leakage. Sure.
Okay, and so basically with the conservation scenario for forest, it wasn't like harvest nothing.
Correct. Yeah. Sorry that I sped through these. The conservation scenario here really is avoided land use conversion. Think of it like that. So I mentioned the switching from a a high land use scenario to a low, keeping forest harvest out of this for a second, right? We're talking about urbanization and other anthropogenic land uses like agriculture. So the conservation scenario here is reflective of switching from a high pathway to a low.
Okay, thank you.
But harvest was by and large kept constant in all of these, with the exception of the CFM. That's the only one that changed the mix.
Awesome, thank you.
Yeah.
Thanks for the question. Who else has got a question? Susan.
Yeah, and Ben, I should know this, but can users or stakeholders develop their own scenarios or scenario assumptions for use in the model? And if they do, how hard is it to implement?
Oh, it's super easy. Yeah, I mean, it's a good question. So we kind of designed this with the idea that we developed some straw man scenarios. But the real idea, and this is kind of the work we're doing for Pyrogens right now, is having stakeholders. There's a whole group of folks that have been working to develop fuel reductions scenarios, for lack of a better term. And so what we're asking them for is, what are the types of activities that you want to simulate? For example, you want to do post-fire reforestation. And so they define their activity. We then ask, well, at what rates would do you want to simulate it? And are there spatial constraints to those rates? And so there's various aspects in the model that we can go in and tweak based on that user feedback. And so that's for somebody that's got virtually no experience modeling. They can provide that sort of feedback to us, and we can change scenario parameters. For people that start to get comfortable in the model, they can go into the UI and actually simulate those sorts of things themselves, framing uncertainty around parameters, changing the rate at which you want to do some sort of intervention, or simply if you don't like any of our developed scenarios, you can create your own and substitute them in and run them against all the other, run them with all the other base parameters that we've got in the model. So it's really designed for users to be able to develop their own scenarios. In fact, we kind of rely on it.
Thanks.
Yeah.
Thanks for that, Ben. And just in the next minute, can you just give us a greater depth about how managers are using these Lucas modeling and the Pyrogens effort that you described for management efforts? So 1 minute, I'll separate that into two things. We've had a number of users with Fish and Wildlife, for example, and other users that came. They were kind of they were involved in the fourth assessment, but not directly in the land use work. But once the land use projections were provided, they realized, wow, looking 100 years into the future of our developed landscape, for example, could answer questions they had in their own work about sea level rise impacts. There was some stuff done down in Fresno related to urban heat island effects in future climate scenarios. We've done some work with Fish and Wildlife where they're updating species status assessments and needed land use, dynamic land use, and land cover as part of their impacts work. We've had a couple of those happen. So it's really kind of, for the most part, been accidental finds that we've had, accidental collaborations that we've had with folks once they see the land use projections into the future. Pyrogens is still, kind of being developed and ongoing. It's a little unclear to me right now how the end products will be utilized. There's a lot of in the other working groups. They're working on some really high resolution fire forecasting stuff. Our stuff, the main use is going to be on
wildfire risk, but pretty broad, right? The spatial resolution of these models is pretty generic. And then also to support these should be the backbone of the 5th climate change assessment from what I understand.
Much appreciated.
Yeah.
Thanks a lot, Ben. Really appreciate it. Okay, we'll move on to the next topic, which is from Jessica Walker at Western Geographic Science Center, talking to us about fire and fuel mapping to inform fire behavior.
Thank you. Yes, I will start with the next slide, please, Lisi. I'll jump into an introduction to fire radiative power, FRP, which is the rate of radiant heat output from a fire, or otherwise known as the fire intensity. And it's measured using thermal channels in a variety of different satellites. When integrated over the complete lifespan of a fire, it has a linear relationship to the amount of biomass burned and smoke emitted, given that FRP is proportional to the instantaneous rate of fuel consumption and smoke emission. Next, please. There are numerous studies of FRP applications and uses in the literature, including its link to legacy effect on carbon dynamics in forests, quantification of fire emissions at various scales, links to post-fire vegetation productivity and mortality, as well as to long-term negative ecological effects, that is to say fire severity. And just a quick side note about the difference between fire intensity and fire severity. Fire intensity is a direct measurement of a fire characteristic, whereas fire severity is an assessment of its ecological impact. And finally, I guess the reference dropped out, but a 2013 paper was able to make inferences about the fire dynamics in Siberian and Alaskan boreal forests based on FRP, and could show that one was more dominated by surface fires than by crown fires. Next, please. Our previous work, which is still very much ongoing, is an investigation of FRP in Alaska, which, as you can see from the graphic there, burns extensively across the boreal forest. In this project, we've been taking MODIS 1 kilometer FRP data from 2002 to present, as well as Landsat-derived 30-meter land cover data. And then we associate the FRP at each pixel with the constituent vegetation types, as well as the reburn history. And in Alaska, we have access to a database of fires from 1940 to present. And then we've been looking at the effect of repeated burns and time since last burn on FRP. And our major goal here is really to evaluate the potential for shifts in vegetation recovery. In Alaska, as in many other places right now, changes in fire regimes to higher severity and more frequent fires have prompted shifts in landscape recovery. In Alaska, the shifts are really setting up the conversion of coniferous to deciduous ecosystems. And another goal is to determine the potential usefulness of FRP for informing active fire management decisions. Next, please. So here's one result of that analysis. This plot shows the proportion of each vegetation type that burned at a particular FRP. And it looks like a complicated plot because of the log-log scale, but the larger takeaways are pretty straightforward. That is that individual classes can be separated by their characteristic FRP signatures. For instance, you can easily see how tundra, if you can distinguish the small blue diamond shape, is separable from higher biomass ecosystems through the full range of its FRP reportings. And at the extreme end of the FRP scale, all you see are the coniferous forest types, black and white spruce. Those are the only ones with enough biomass to burn at those intensities. And this really gives us confidence that FRP is consistent and informative enough to use on a vegetation-specific basis. Next, please. Another result of the analysis looked at FRP response to repeated fires. And here, what we expected to see was a fall off in our FRP with a greater number of burns. That is, as more fires swept through an area, you would see a decrease in biomass buildup and thus a lower FRP. And this is really hinging on the characteristic of fire dynamics in Alaska, in particular in the coniferous systems, where a fire goes through and really burns everything in the system. There's not a lot of standing debris left. And that hypothesis turned out to be true in some, but not all of the vegetation categories we've looked at. Next, please. So how could we apply this analysis to California? There are many commonalities between California and Alaska that would make it an easy transfer of geographical focus from Alaska to California. One is the fact that, as in Alaska, California burns quite a lot, and that the fire regime seems to be shifting to a higher severity, higher frequency type of cadence. And in California, that also sets up the potential for vegetation community shifts, although in California, obviously, it would be much more likely to be along the lines of forest converting to something like a grassland or shrubland system. The complications that are specific to California is that it's a complex and diverse landscape, presumably much more so than Alaska, and also that there are active fire suppression activities, which is not the case in Alaska. Pretty much fires are just allowed to burn, and that could potentially affect the reportings of FRP in these areas. Next slide, please. In preparation for this talk, I took the analysis that we had done for Alaska and moved it over to California. And so here are some preliminary results of those same plots that I've just shown. And in the comparison of FRP for different vegetation types, what you can see are similarities in terms of the results. And here we had larger aggregations of grassland, forest, and shrubland, which are larger catch-all categories for a great variety of different vegetation types. But you can see here too that there's a distinction between them, and they really, again, show the same dynamic, which is that the highest biomass categories, that is to say forest, are the only ones that are burning at the highest FRP values. Next slide, please. In terms of the FRP response to repeated fires, the pattern here was quite different than Alaska and took me back a little bit to try to figure out what's going on here. What you see is that in terms of FRP relationship to subsequent or to successive burns, there's really an increase for at least through the third fire in shrubland, fourth in forest, and then for grassland, there appears to be simply a monotonic, essentially increasing FRP with successive burns. And again, this will hinge on the types of dynamics of the fire in the relative categories. And what you would expect in these types of fires is that there's much more standing debris, which turns into fuel for successive fires. And thus, you're seeing this type of dynamic. Next, please. So how could we use FRP in California to better manage forested landscapes? The same general goals and applications would apply in Alaska as in California. That is to say that in an era of increasing frequency and severity of fires, we want to be able to make predictive estimates about the character and impacts of future fires. So if we know how historical conditions affect fire intensity, as well as the effects of current land cover types and conditions, and particularly we have links to how fire intensity affects future dynamics, we can begin to make more informed assessments of how future landscapes will respond both during and after a fire. The knowledge also gives us the means to estimate fewer emissions outputs. Next, please. So looking forward, there are a great many different research avenues to explore. The first is to tighten the link between specific vegetation types and FRP. Again, we've shown that there are consistent patterns among the individual ones, but we want to be able to make sure that there are consistent results for the individual land cover types. The investigation of time since fire effect on repeated burn outcomes is an important aspect so that we not only have the effects of repeated fires, but we have the effects of those of the sequence of fires as mediated by the intervening time between fires, because obviously the more time there is, the more opportunity for a buildup of biomass that could translate into a higher FRP for the subsequent fire. Obviously, the linkage of FRP to longer-term post-fire outcomes is extremely important. And again, there's that desire to figure out how a landscape will react, not by waiting 20 years to see how it develops, but by making some sort of assessments based on fire characteristics and land cover types and condition. The incorporation of climatic conditions is an incredibly important aspect that we have yet to explore, so that will definitely be integrated into our future analyses. And finally, we'll be testing the applicability of different sensors. There are higher spatial resolution data sources that we can tap into, among them VIIRS, as well as higher temporal resolution geostationary satellites, and each will give us data that can be complementary and helpful for future analysis. And that's all I have. I'd be happy to take questions.
Nice work, Jessica. Thank you. Who's got questions for Jessica? Loretta.
Hi, Jessica. Can you hear me okay?
I can.
Great. So thank you for that great talk. It was very good content, and I'm still absorbing it. So forgive this question if it's abundantly obvious. But on your looking forward item, link the FRP to longer term post-fire outcomes. I was hoping you could drill down a little more on that, because I'm not sure if this relates at all to, we wait for severity maps to come out. There's a latency there, but we're trying to understand, the state would like to have an earlier read on really, after these fires, we're getting ever more frequently and more large fires. It'd be nice to get an earlier read on what we might expect. Granted, waiting for those severity maps is important. I was wondering if you think that this FRP, insights from FRP could sort of provide interim insights for the state, and in what ways, in terms of management, response, and so forth. I don't know if that makes sense, but I'm trying to see if this FRP data can give us early reads, and to be more responsive sooner and have a better appraisal of conditions out on the landscape.
Exactly, and that is one of the aspects of this particular analysis that we're trying to figure out. Coming from Alaska, where a lot of the landscape conversions are predicated on the amount of organic soil matter that's been burned, which is not necessarily something that satellite fire severity picks up. FRP seems to be much more of have much more potential to give us information that can be immediately useful in predicting the potential for a landscape conversion. And again, in Alaska, it's predominantly from coniferous to deciduous. In California, I would imagine that, again, fire intensity is just yet another angle on fire impact. And so it would have potential for giving you information that could feed into, hopefully, quicker predictions of how the landscape is going to respond to a particular fire.
And can I ask a follow-up on that? I don't know if I had a sense of the temporal and spatial application here. Like, is this something you can? I think you deployed this analysis statewide for California preliminarily. So is it kind of a statewide frequent thing that can be done? These satellite data are updated pretty regularly, right? So in other words, we could run this analysis frequently if we wanted to. Is that right?
Exactly. So the MODIS data that I was using returns essentially 4 looks at a particular area of the landscape per day. And all I've been doing is taking one of those, and I've been taking the max FRP for a particular reading on the ground. And I've been using Google Earth Engine, and I believe the lag for updating MODIS data is on the order of a few days, possibly less. If anyone knows that for certain, please chime in. So yes, the potential for updating it on a more frequent basis is definitely there.
Thank you.
Absolutely.
Thanks for the question. We've got Keith Miles with our Western Ecological Research Center.
Hi, Jessica. Thanks so much for your presentation. I was just curious of a couple of things. One in Alaska, is there evidence based on historical record that what you're seeing there is unprecedented? And what makes you think about that is what we've seen in the sequoias in the Sierra Nevada, that some of the fire-related events affecting the sequoias is unprecedented in, say, a past 1,000 years from what we know of the historical record of the sequoias. So that's my first question. Maybe you can answer that, then I can ask a second question.
I would hesitate to give an answer to that question simply because sequoias are not my area of focus, and I do not consider myself very well educated on their particular fire dynamics.
Well, I was asking about the boreal forest, though. Those changes there. Is there enough information to say that those changes that we're seeing now, have they occurred in recent, maybe by recent I mean the past 1,000 years history, or is this unprecedented in the boreal forest?
I can say with confidence that it's what we're seeing currently is unprecedented in the past 100 years. From what I've read, it appears to be anomalous in a time period that's longer than that. I would, again, be hesitant to stake a firm claim to whether or not 1,000 years is something that has not witnessed this type of behavior. I can only speculate, unfortunately.
Okay. And then my second question is you had your modeling having California go from forested to grassland, shrublands, but I would assume by the forested you mean that they would go from a current community structure of forest to maybe a different community structure of forest like we're seeing in the coastal redwoods where there is invasion of conifers into the redwood zones. And is that what you were inferring, though, is that there would be multiple changes in the forested states like to oak or juniper, and then eventually going to shrublands or grasslands?
Exactly, and I think I extrapolated a bit too much from my experience with what we're seeing in the Southwest, in particular in the ponderosa pine communities, where we are definitely seeing a replacement of the original taller statured forest with shrubland or grassland. But in essence, the principle is the same, that these sorts of changes in fire regimes are having an effect on the replacement vegetation trajectories in a way that veers them away from the original burned material towards something that is, whether it's a permanent replacement or a longer term sort of temporary holding pattern before it gets back to the original is unknown, but it's definitely not coming back to the original ecosystem.
Okay, great, thank you.
Thanks, Keith. Nadia Tace with CAL FIRE's next.
Hi, yeah, I was going to ask a similar question as Loretta, but on a little bit different angle. Can you go backwards in time and also couple it with other data sets like previous fire perimeters and previous treatment data to kind of get an understanding of the resulting burn severity? So you've been talking about understanding longer term post-fire outcomes, but also understanding the actual fire outcome itself as it related to previous, land management and disturbance history.
Exactly. And right now, all we've really done is look at the history in terms of previous burns. We haven't looked at, say, management activities that have, such as thinning or any other activities that might have influenced the FRP. We can only go back to the extent that we have, obviously, fire perimeters to work with. So for California, I believe it was 1878 is the first one that I saw in the database I've used. And again, we're limited to data that's considered to be reliable. So that's not necessarily the starting point that we can work with. But definitely the investigation of how more sort of nuanced activities on the landscape have affected a recorded FRP for a particular land cover is of great interest to us for exploring further. Did that answer your question? Sorry if I kind of got away from what you originally wanted me to tell you about.
Yes, thank you.
We have maybe a minute or two for one final question. Anyone else have a question for Jessica? I'll ask a question then. Well, it looks like there's a chat here. We'll wait for on that chat. Jessica, you mentioned looking forward that you'd like to incorporate climatic conditions. Can you give us a sense of what you suspect that does to FRP?
Exactly. So one very concrete example is that simply prevailing wind conditions can have an effect on the measured RFP. FRP, sorry, in particular ecosystem types. And I believe the study focused on grasslands in particular, but since it's a measure of the fire intensity that is obviously affected by things like moisture or anything that would affect the condition of the fuel to be burned and the conditions under which the fire is happening. So incorporating something like the preceding amount of moisture that had fallen upon a particular area before it burned and how dry that fuel was will be information that's going to again feed into the eventual FRP value.
Okay. Jessica, thanks so much for a great presentation.
Thank you.
And we'll shift to our final presentation. Last but not least, certainly, is Adrian Doss. And Adrian's with the Western Ecological Research Center, and he's going to be talking to us about assessing forest vulnerability in an area of severe drought and catastrophic fire. Adrian.
Okay, well, I'm going to get my timer going so you don't have to yell at me, hopefully, later. But so I'm going to talk about a few of the projects that our shop is working on that we thought would be of interest to this group. But first, so next slide. So I wanted to briefly stop and talk about a context. It's a context we all know about, but it really frames the kind of research projects that I'm going to talk to you about today. And so California's just been through, maybe is still in one of the most severe droughts in at least centuries. This resulted in an enormous number of dead trees, which means an enormous amount of fuel. And we're now seeing fires that are being, these really unprecedented types of fires that are causing unprecedented types of fire effects. As Keith mentioned, we're seeing giant sequoias that are supposed to be fire adapted, whole hillsides of them burning up in some of these events. So next slide. So this sort of frames the work that we're doing the work I'm going to talk about. The first project is the Mixed Conifer Vulnerability Project. And the idea there is, can we give you a tool that will tell you when you have a severe drought where you're most likely to get all these dead trees? And then the Fire and Fuels Project, the idea is, so can we tell you which parts of your landscape are at most risk for these catastrophic, unprecedented types of fires? Are there places that you can target treatments to try to minimize that? And then briefly, I'm going to talk about a treatment effectiveness project. Phil talked a little bit about some of the work we've that he's led and collaborated on. There's another project that I think is worth bringing up. Next slide. So the idea behind the Mixed Conifer Vulnerability Project is that you have this drought was a really severe stress on the system. And if you want an empirical way of detecting where your system's most vulnerable, when it's under a lot of stress is a good time to do that. And what we did is working with the Global Airborne Observatory and folks from the U.S. Forest Service Region 5 Remote Sensing Lab. I think I saw Michelle Slayton in the audience out there, so she's one of the folks we're working with, is to take some high-resolution hyperspectral data that we had available that was taken during the drought, and some really high-quality ground-based data to build these survival models that will predict vulnerability on the landscape. And the models fit and worked out pretty well, but the second step was seeing whether they really worked. So we collected a really big data set in this 260 square kilometer area where we said, okay, let's go get some trees that we didn't use in the model, and we said what the likelihood of them dying are. Did they die at the rates that we said they would? Next slide. So on the left, you have a model output from one of these tools. And basic idea here is that that's the remote sensing flight box, and more red colors are places that are more vulnerable, where you'd expect to see more mortality during a drought. And these are the kinds of outputs that we're working with the managers locally here to give them so they can use to prioritize places to manage in their landscapes. The right is the validation, and I'm trying to be careful not to spend too much time on graphs, but the basic idea here is the x-axis is what we predicted would happen, what the proportion of trees in a given category would be, how many of them would die, and on the y-axis is how many did die, what proportion did die, and that solid line down the middle is a one-to-one line would be a perfect fit. And this is just a really good, surprisingly good fit. And it's even better than it looks because most of the data are actually in the upper right-hand corner there. So the model worked really well in validation. Next slide. But obviously, this is fusing some high-resolution data at Sequoia and Kings Canyon National Parks. That's where I'm based. What we'd like to do, obviously, is expand the geographic scope of this model. The best way to do that is using satellite data, so Landsat data at 30-meter pixels. We have a better spatial and temporal coverage when we use those data. And we're already I'm in discussions with the Forest Service, folks at Yosemite, to get more data to validate these models against the satellite data. There's not a good reason to think they won't work, but I've learned from experience that you really need to test and validate these sorts of tools when you start expanding their use. Using the satellite data also lets you expand the temporal scope. So I had mentioned that the idea is that we're looking at these systems when they're under a lot of stress, but it would be awfully nice to be able to look at them when they're not under a lot of stress and progress, and look, can we see, relatively speaking, those vulnerable parts of the landscape even during what hopefully will be normal years again. And we also want to improve the models. The upside of a 10-minute talk is I don't have to go into all the weaknesses, but there are obviously situations and there are species mixes and circumstances where they don't work as well, and that's something we're working on. Next slide. That leads to our fire and fuels project, and I was very gratified that Ben talked about pyrogens because this involves them a lot. But the basic idea is we have had over a century of fire suppression that has allowed fuels to accumulate on these landscapes, and we've just put in an enormous amount of heavy fuel through this drought mortality. Conditions are, are like unprecedentedly dry, and that's resulting in these really big fires. And if you're a manager, say at Sequoia National Park as an example, you want similar maps that tell you, well, which parts of my landscape are most at risk? And you want them at a scale that you can use as a manager. So one of the things you fear is that there are statewide groups working on these next generation fire models. They can start predicting the behavior of these fires because current fire models don't do a good job of it. But what you don't want as a manager at Sequoia is a big red box on your park that says, yeah, it's bad here. What you want is something that you can actually use. So next slide. So we're collaborating with pyrogens to provide them really high quality data. We're using Sequoia National Park as sort of a test site. And this is, again, a collaboration between the Park Service and the Forest Service, primarily the remote sensing lab. And what we're going to do is work with pyrogens to give them really high quality, high resolution data, fuels data that they can use as they're building to their models to hopefully improve that development and also ensure that managers locally are going to get the outputs that they can use. Next slide. And just to give you an idea of the kinds of data we're collecting, so I'm showing you the same flight box where working with the RSL, we're developing these dead tree maps. So where are all these dead trees? And we've got a couple of flight boxes actually, and that this work's ongoing. We've been working on this for a couple of years now. We're obviously going to need to move outside those high resolution boxes to work with satellite data. Heads up, Michelle, we're going to be working out with Landsat data to get dead tree mapping done in other spots. And then what's ramping up in the next year is our surface fuels mapping. And the Berkeley folks who work with pyrogens are developing have developed some fuels protocols that they're going to use to feed into these next generation models. We're going to be using those. So we're going to be mounting a pretty big effort to get that data on the landscape. And next slide. Thanks, Michelle. I'm glad. I think I warned you before. So it's a growing project. Obviously, there's a lot of interest in this stuff. And so next. So we obviously had last year one of these fires burn right into the Sequoia National Park and into some of these sequoia groves, and saw some really unprecedented effects. Like I said, whole hillsides of giant sequoias burning up in a day. And we're hoping to use this information. We're gonna mount an effort inside the Castle Fire footprint to look at what we knew about the forest structure beforehand, what in places, because even inside a fire like this, there is low, medium, and high severity patches. So we're going to collect some data to see if we can create at least short-term tools to help managers look at what places look bad what places ended up having bad effects during the fire, and see if we can apply that to other parts of the park and sequoia groves that haven't burned. Next. And there is some focus on sequoia groves here because of some of the things that we're seeing. It's a high priority management target, but obviously understanding fire risk, even for sequoia groves, really means understanding fire risk for these forests as a whole. Next. And obviously the goal is to expand this sort of project into additional landscapes. We're using Siki as sort of a test site to see how practical it is, how well can we do at producing these models. And the pyrogens modeling is something that's been going over. It's going to happen in stages over a period of several years, and we're going to be working hand in hand with them while they do that. Next slide. So Phil talked, for those of you who were there, I think Phil talked about some of this work that he's been doing, looking at the effectiveness of treatments and prescribed fire and, drought effects. He and I are working also on another project where we're going to use satellite data, use remote sensing indices to detect changes in the landscape. And then we're going to pair that with data from thousands of plots that we've gathered, where we have forest structure information, we often have treatment information, and just ask the question during the drought, how well did these treatments actually work at this broad scale over the central and southern Sierra Nevada? The first part of that is showing that these remote sensing indices actually work. And that left graph, we've actually completed that. They do work with some caveats, and the next stage is going to be extrapolating to these other places. Next. But I want to just briefly mention, as we're talking, and these multi-agency groups are talking, one of the challenges we've run into in this project is what's a treatment? And that seems to vary quite a bit, and it's not always quantified systematically. And I think as a group, we really need to think about having a systematic way of approaching what treatments are and how they're quantified, so that we can start answering these questions, not just did the treatment work, but what kind of treatment, to what extent, and to what degree of protection do you get with it? And next slide, but that's it for me. Hopefully I didn't talk too fast, but I'm here happy to answer some questions.
You did great, Adrian. No yelling necessary at all. We've got a chat from Loretta, and she's asking, what does the forecasting horizon look like with your models?
So so that's a good question. So for the mixed conifer vulnerability model, we're looking at that model was basically a survival probability model that you did 4-year survival. And that was pretty important, actually, because, bark beetles attack a tree and the tree might still look green, and you can detect that tree's dying, but all you're doing then is just detecting trees that are already dead. So it's pretty important to us to be able to show that we were not just projecting trees that were already in the process of dying. We're looking at what the risk is over a several-year period. So the models right now are designed around a 4-year horizon if you're experiencing severe drought stress. For the fire and fuel stuff, that's a better question for the experts at Pyrogens, but I know the goal is to do things like model fuel accumulation. So they've got models, they've used a lot of data from our area actually, but looking at tree fall rates and modeling decay. So those are going to be longer term projections and hopefully dynamic ones that show you your risk through time.
Thanks, Adrian. Adam Moreno has a question.
Hey, Adrian. Yeah, thanks for that presentation. Great work. Super interesting. So I wanted to ask about the vulnerability maps. And so I like that now you're going and you're trying to study the effectiveness of management treatments on drought vulnerability. Right, because, there are multiple vulnerability maps or, analyses that go on, but then it's like, okay, so what, right? As a manager, you go in and it's like, okay, this place is vulnerable. What forest structure do we need to change so that it's not vulnerable anymore, right? Is it always just about reducing density, or should we lower the canopy height, or is the species just wrong now, or is the stand too old, or, whatever. So I guess this is maybe more of a suggestion, than a question. But as you're going along, with your treatment study, bringing it back to that vulnerability map and then saying not necessarily maybe what management action to take, but what forest structure needs to change, I think is a good way of looking at it. Because maybe on a statewide scale, we don't want to dictate this is the management action you should take, but we just say this is the structure that maybe needs to change. As a manager, you can figure out how to go about that in doing whatever management action you want. Anyway, thanks.
No, I agree. I think what you're pointing out exactly where, one of the research area highlights that we need to move into, because we talk about density management. Obviously, that has an effect, right? Reducing the number of trees is supposed to increase the resilience. But there's also, questions of species mixes, because you've got, a pines. You can make a fairly low density pine stand and still have a bark beetle, bark beetles ravage through it. There's a lot of questions to ask about what's a resilient forest structure, and a question at which point how long can you hit the density button, right, before you're just looking at like a grassy woodland with a few trees in it? And so what are the practical ways we can go at it? What are those forest structures? And to some extent, it's bed hedging, right? There's a stochastic, there's some probabilistic things that are going on. Did you get a bark beetle outbreak in that area? And those things, there are other things going on to predict those, and we're not great yet. That's an open area of research for understanding what makes an area more susceptible, beyond just density, because there's more dynamics going on there than just how many trees there are. But anyway, I could go on about that for a long time, so I won't, because I think there'll be other questions.
Thanks for the question, Adam. Susan Benjamin chats a question. Is anyone comparing results of castle fire on Sierra sequoias with lightning fire on coastal sequoias? And then Keith is after that.
I don't know. And those systems are so different, and those trees are actually so different in how they behave and their ecosystems, that I know that, general discussions about redwoods and how they function in different places have been done. I don't know if there's a direct comparison, in part because the systems are really different beasts, at least right now.
Thanks, Adrian. Keith, you're up.
Nice presentation, Adrian. I'm just curious, because I feel a John Keeley in the back of my ear somewhere asking this question about, how much of this, what you've learned, has been derived from the historical record? How much of this is just brand new? It just brings a question of curiosity, because I think a lot about the Sierra Nevada Ecological Project, and we're probably 15 years ahead of what it predicted. In terms of what we're seeing in the current fires east of Sacramento right now. So just from your viewpoint, is there any of this history repeating itself because of what we know from the historical record, and what's new?
My current work right now is, we're using data right now, what's happening right now, to develop this modeling. But understanding what that means really is the context of the previous research. And there's a couple of things to think about. It's not new that people have been saying that work in these forests have been going on for decades, talking about fuel accumulations and increased densities, and if things are going to get warmer and drier, we're going to start getting really severe fires. It's important to note that that's the context, right, in which we're doing this research. But the other tricky thing is the work in mixed conifer forests and conifer forests in the Sierra for decades, was, hey, we need fire in these systems. We want to restore historical forest structures. What they're, the target was the late 1800s. But we're now in a place where we're seeing things, and we're in climates that with those that are not the late 1800s. And so that range of variability gives you the context for understanding the severity of the change, the kind of vulnerability that you're looking at. But it's an open, ongoing discussion with managers about what does that mean for what we're targeting. Are we trying to protect? How much is protection? How much is easing transitions? And what can we do to hedge our bets against what was in the past and what we're probably going to see going forward? I don't know if I'm answering your question exactly, Keith.
You did. Yeah. Thanks much, Adrian.
Thanks for that question, Keith. Cynthia Wallace chatted a question. She asks, is the carrying capacity of forests known or defined given characteristics like the type, aspect, climate, soils, etc.?
So there's definitely work that's looked at productivity in a given site, and foresters done a lot of work looking at what a site capacity is. The thing is, that question, right? That question, you have to frame your assumptions. So there's a certain degree, if the forests go and you put out all the fires, obviously they can support more density than they did historically. But given the kind of fires you get, if you allow things to reach what might be, say, just a raw carrying capacity, means it's not really sustainable. So what is the carrying capacity given the context of the disturbances you're likely to see? But there certainly has been a fair bit of work, and I'm not the expert on this, looking at site productivity curves and that sort of thing. So people definitely look at how much they can grow on a site. So there is some information about it. But a lot of the below ground processes, we don't have good we don't have a good feel for, understanding the soils and the depths and where water is moving on the landscape, because what the carrying capacity is really varies even, within fairly small, fairly short distances.
Thanks for the question, Cindy. Loretta's next.
Hi, yeah. I just wanted to say that I really think the work that you've done, and actually the whole team today that's been presenting is just, it's captivating. It's great to know in a little more detail what you're up to in this space. We have a lot of knowledge and data gaps that we've identified across state agencies in this space, particularly some of the material you just covered. And so I just want to flag for you that the treatment effectiveness, not just limited to vulnerability around drought, but also wildfire components, doing a retrospective analysis, kind of a big data retrospective analysis is of interest. The other piece is looking at, so treatment effectiveness, but also looking at the, what was the other piece? I just lost my thought. I apologize. Yeah,
okay.
The early warning sort of, well, we're kind of in the space of looking at it, developing out an early warning system for, drought and onset of mortality, not just drought related, but other factors. And so I just think it's great to hear a little more about what you're digging into, and possibly we should tie in with your team and conversations we're having with NASA and Forest Service about this. So just thank you for coming forward and sharing your work on this.
Oh, I appreciate that, and I really agree. There's definitely a lot of synergies to the work that's going on right now. I mean, yes. So the answer is absolutely. I agree. We should be doing that, because I think the opportunities to build out what all of us are doing more broadly and more generally is really strong right now, because we all have some of the same questions.
Thanks for those comments, Loretta. Keith, you've got your hand up.
Yeah, I just wanted to comment that it's become apparent to me, and it's fun hearing Adam ask questions, because he doesn't know it, but my spouse works for Cal Air Resources Board. So I actually asked some questions about him and got really good responses from her. And it's just interesting that we're probably doing a lot of carbon storage type work, carbon availability type work, lots of work in forest health, forest management, and we are available. And I have to speak for the ecosystems, but I think I'm speaking for Susan Benjamin and Colin Williams and the other center directors. We're available to provide a heck of a lot more, either in just providing the published documents, but also having future interactions where we can present to your staffs to give you a little bit more in depth, to at least let you know the wealth of information that we have that's available to the public, and that public includes the state. Just wanted to make that comment.
Yeah, this is Susan. I agree with Keith, and we're happy to discuss things in greater depth with people who are interested in a particular topic, and see if we can get some clarification and collaborative research going.
Thanks, Keith and Susan. We probably have time for one final question if someone has one for Adrian, or for anyone, frankly. Okay. Adrian, thanks so much for a captivating talk.
Thank you.
And to all the presenters, thank you for all the work you put into this, the time today. To all the attendees, to spend a couple hours with us discussing the latest that USGS is doing and how we might be doing it better. Thanks to Alicia Torregrosa, as always, for the work she's done to help with the logistics on this meeting. We couldn't have done it without you. And if there's any questions people had but they didn't have a chance to ask them, there's a list out there of emails from all the presenters and the biographies. Please access that. Feel free to connect with anyone that's presented or anyone that's attended, frankly. And if you don't have their information, you can contact me and I can get it to you. Our objective here at USGS is to produce analytical tools that improve your ability as managers to make informed decisions. So if you see a way we can do this better, please let us know. That's why we're here. So I'll turn it over to Loretta for any closing remarks of her own.
Thank you, Darrin, and the entire USGS team again for excellent presentations. And Darrin, I just thought maybe it'd be worth for some of the folks on the call that are not plugged into the next presentation, I think it's next week, what that will cover and when it is.
Right, yeah. So next week's presentation is on Wednesday, and I think I better find it here. Wednesday at 2 o'clock. And if anyone does not have that invitation, let Loretta or I know. We can forward you that. We would welcome anyone.
And that's to do with hazards principally, right? Isn't that
That's
the post-fire?
hydrology, actually.
Oh, excuse me. Yeah. Okay.
Yep.
Yes. It'll be hydrology focused, but there's always so much overlap and integration. So I'm sure everybody on this call would find it interesting as well.
Absolutely. Thanks for that, Loretta. Okay. Well, thanks everyone. We've received a couple questions regarding the recordings for today's presentations and Tuesday's presentations. We have them. We're scrubbing them a little bit. We're annotating them so that folks can easily access any given presentation. So give us until next week, and we'll send those out so people can look at whatever's interesting to them. So thanks a lot, everyone. Have a great weekend. Take care.
Thanks, Darrin.
Thank you.
Thank you. Bye-bye.
Thank you.